Hi, this is Mr. Barron. I'm going to be teaching you about acids and bases, and in the process I'm going to be doing a couple of problems from your homework set. Number one. When it comes to acids and bases, don't forget there are two definitions for acids and bases. Imagine you have a hydrochloric acid molecule, and it drops into a beaker. And this beaker is full of nothing but pure H2O. Well, as soon as that HCl hits the water, it ionizes, which is another way of saying it dissociates. And that's because HCl is a strong acid. It completely ionizes in a solution of water. So we can use an equation to represent the change that's just happened. And it's HCl breaking apart into H plus and Cl minus. H plus, how many hydrogen ions in your solution? The more of these, the more acidic it is. So don't forget, we call these protons in chemistry because a hydrogen atom with one less electron, which means it has no electrons, is nothing more than a proton. But you'll hear me refer to them as hydrogen ions. There's another way you can view this acid dropping into the water. So in the same sense, you can view the change like this. Hydrochloric acid bumping into water, and the hydrogen does fall off, but it immediately sticks to the water and forms this thing called a hydronium ion. So this we call hydronium. Now, hydronium and hydrogen ions, the thing is that these are interchangeable when we're describing the acidity of a solution. So in all the equations we deal with, you'll see them either written out like this, where you have the concentration of hydrogen ions times the concentration of hydroxide ions, or equally correct would be K sub W, and then you have hydronium, H3O plus, or OH minus. So this is what we call the Arrhenius definition, and the Arrhenius definition of an acid is basically that they break apart and then you have these hydrogen ions. But in reality, these hydrogen ions don't stay by themselves in water. Those hydrogen ions immediately stick to water and form this thing called hydronium. So this perspective that a hydrogen is actually transferred from the HCl to the water is what we call the Bronsted-Lowry definition for an acid. So anyhow, just know that these two symbols right here, the H plus and the H3O plus, those are interchangeable in all of the equations that you'll see in this chapter. So for all of these, you'll see H plus, but on your AP test you may actually see H3O plus. Just keep in mind, again, they're interchangeable. So with that definitions of acids and bases, let's talk about problem number 37. So problem number 37 from chapter 16 gives you a table. And in this table, you've got H plus, OH minus, and by the way, each of these are concentrations in molarity. And then you have pH, and then you have POH, and then you have to identify whether the solution is acidic or whether it is basic. All right. Now, the table starts off with the very first row giving you information about the hydrogen ion concentration, which is 7.5 times 10 to the negative third molarity. All right. So you have to fill in the rest of the information within the table. So there's a couple of key equations that we're going to be using throughout this entire chapter. So I'm going to draw a line separating out the table. And the most important equation to know is that there is this constant for water. When you have pure water, the hydrogen ion concentration times the hydroxide ion concentration is always going to equal 1 times 10 to the negative 14. What this will allow you to do is that if you know how many hydrogen ions are in your solution, you can then figure out how many hydroxide ions there are in the solution. Because the hydrogen ions times the hydroxide ions will always equal 1 times 10 to the negative 14. So what we're going to do is, and very important, this is very important to remember, this is only at 25 degrees Celsius. All right, now, another equation that we have to be familiar with is how to figure out pH and POH. pH, the P means negative log, so it's the negative log of, and since it's H, the hydrogen ion concentration. POH is the opposite, which is the negative log of hydroxide ion concentration. And don't forget the pH scale goes up to 14, so if you take your pH and add it to your pOH, it's always going to equal 14. So for figuring out all the unknown information in this question, you have to use this equation, and this equation. You really won't need to use the pOH as long as you know this very important one, that pH plus a pOH equals 14. All of this is in the equilibrium section of your equation and constant sheet. All right, so let's begin with the math now. Now what we have to figure out is the hydroxide ion concentration. So to figure this out, I'm going to take my hydrogen ion concentration and plug it in right here. So let me show the work that I'm going to be doing for this particular problem. I'm going to put it in a little box. 7.5 times 10 to the negative third molarity, that's my hydrogen ion concentration. I don't know my hydroxide ion concentration, that's unknown. And I know that it's always going to be equal to 1 times 10 to the negative 14. Okay, so that means I just have to divide by 7.5 times 10 to the negative third on both sides. And once I do that, I will know my hydroxide ion concentration. And by the way, this really should be brackets. So 1 times 10 to the negative 14th divided by 7.5 times 10 to the negative third gives me a hydroxide ion concentration of 1.3 times 10 to the negative 12th molarity. Now we have to figure out the pH and the pOH. To figure out the pH, I'm going to use this equation right here. pH is equal to the negative log of hydrogen ions concentration. So I take the 7.5 times 10 to the negative third and take the negative log of that in my calculator. So negative log of 7.5 times 10 to the negative third, I find out that it's 2.12. Okay, now to figure out pOH, I'm going to use this equation down here. I plug in my pH, 2.12 here, so it's 14 minus 2.12, and I get my pOH of 11.88. Now, to figure out whether something's acidic or basic, I recommend just always using what you've learned in middle school, which is that if your pH is below 7, it's acidic. So don't forget you've got that little pH scale where you got 14 one end, 7 is neutral, down to 0 on the other end, and then on this side it's acidic, and on this side it's basic. Oops, let me show that. So don't forget 7 is the cutoff point. So because this number is below 7, we are in an acidic solution. Now the next problem that we deal with begins with the next row in this table is 3.6 times 10 to the negative 10th, and then you have to figure out the other unknown information for this. It's the same thing that you just did previously. You're going to have to figure out the hydrogen ion concentration, so you're going to use this equation right here, where you're going to plug in the 3.6 times 10 to the negative 10th into that OH minus, so it's 1 times 10 to the negative 14th divided by this given information, and then you find your hydrogen ion concentration to be 2.78 times 10 to the negative 5th. Now to find the pH, you just do it the same way you did before. You take the hydrogen ion concentration, take the negative log of it, and then your pH is going to be the negative log of that hydrogen ion concentration. Now I'd like to show how to actually do this in your calculator when you're using the negative log. So I'm going to hit negative log and then that 2.78 times 10, and I'm using the E button, of course, times 10 to the negative 5th, enter, and I get my pH of 4.56, which is still below 7, so I know it's going to be acidic. And to figure out what the pOH is, remember, pH plus pOH is always going to be 14, so 14 minus 4.56 is going to give us 9.44. All right, now the next row gives you given information on pH. It tells you it's 8.25, and you have to figure out the hydrogen ion concentration, the OH minus, the pOH, and whether it's acidic or basic. Now this time, let me do this problem on another piece of paper here. So this is our given information. We know that our pH is equal to 8.25. And what I want to figure out is the hydrogen ion concentration, the hydroxide ion concentration, and so forth. So I know that pH is equal to the negative log of the hydrogen ion concentration. So what I'm going to do is write this out one more time, this time without writing out the word symbol pH. So 8.25 equals negative log of hydrogen ions. Since this side is negative, I'm going to multiply both sides by -1. So you get negative 8.25 equal to positive log of hydrogen ion concentration, because the negative times the -1 obviously becomes positive. So now I have to solve for this. Let me show you how to do this in your calculator to save time. Don't forget, these logs that we're dealing with acids are always going to be base 10. So a shortcut for calculating this would be, in your calculator, watch how I do this. I'm going to take the anti-log, which is 10 to the x, negative 8.25, cap off my parentheses and hit enter. And that's my hydrogen ion concentration. So my hydrogen ion concentration is 5.62 times 10 to the -9. And that's going to be molarity. And that right there is your hydrogen ion concentration. So once you know your hydrogen ion concentration, you can use the same steps that you used before in this table to figure out the hydroxide ions, to figure out the pH, pOH, and whether it's acidic or basic. I'm not going to show the rest of this problem and given a setup on this. Don't forget your basic Algebra 2 skills with logarithms. Now we're going to be doing another problem, and the next problem I'm going to show you is problem number 43D in particular. So problem 43D tells you that you have to figure out the pH, and you're given information on mixing two different solutions. One solution that you start with is 10.0 milliliters of 0. Let me make sure I write this one right. 0.100 molarity HBr, and then you're going to mix that with 20 milliliters of 0.200 molar HCl. Okay, so in this question, you have to figure out the pH after you have this solution mixed with this solution. So let's, again, refresh our memory about what the formula for pH is. pH equals the negative log of hydrogen ion concentration. So if I want to figure out what the pH is, I have to know my hydrogen ion concentration. So let's look at what the amount of hydrogen ions are in this solution and this solution when I mix the two together. So let's take a look at this one. I have 10 mils, which is the same as 0.01 liters. Okay? So 0.01 liters. If I can figure out the amount of moles of HBr I have, then I know how many hydrogen ions are going to come from it. That's because HBr, don't forget, this guy right here is a strong acid. You have to memorize the strong acids for this chapter. The strong acids include HCl, HBr, HI, H2SO4, HNO3, HClO3, and so forth. You have to memorize the strong acids. HCl, conveniently, is also a strong acid. So that means that they completely ionize in solution. So however many moles of each acid I have is the same number of moles of hydrogen ions that I begin with. So for this first solution, it's 0.01 liters. And then I know the concentration, which is 0.1. And don't forget that's molarity, which is the same as moles per liter. And that will tell me the amount of moles of HBr I have. So 0.01 times 0.1, you do the math and you end up with 1 times 10 to the -3 moles of HBr. Now, I have to remember that this completely ionizes. Since it fully ionizes, the amount of moles of HBr I have is the same as the moles of hydrogen ions for that first solution. Okay? So I'm going to put a box around that because I need to remember that. So that's just for the first solution. Let's talk about the second solution that I'm mixing together. The second solution, I begin with 20.0 milliliters, which is the same as 0.02 liters. Do the same math I did on the previous one, so it's going to be 0.02 liters times the molarity, which, don't forget, is going to be moles per liter, so your liters cancel out when you do the math, and you end up with, when you do 0.02 times 0.2, 4 times 10 to the negative third moles of HCl. And don't forget, because it's hydrochloric acid, it's a strong acid, it fully ionizes, so you actually have 4 times 10 to the negative third moles of hydrogen ions. So I know when I mix these two solutions, I have this many hydrogen ions plus this many hydrogen ions. So I'm going to take both of those hydrogen ions and I'm going to add these two together. The reason I want to add those two together is because I want to find the total amount of hydrogen ions in the solution. Remember, I have to figure out the ultimate pH. So when I add those two together, I get 5 times 10 to the negative third moles of hydrogen ions for this total solution. That's for your total. Okay? Now, remember, what we plug in to find the pH, let's go back to the pH formula. This has to be in concentration. Everything in brackets has to be in concentration. I just have moles of H+. Notice it's not in brackets. So to figure out its concentration, I have to know the total volume. That's not 10, it's not 20, it's 10 plus 20, which means I have to take 5 times 10 to the negative third moles and divide it by the total volume, which is 30 milliliters, so it's 0.03 liters. And that's going to tell me my concentration of hydrogen ions. So 5 times 10 to the negative third divided by 0.03 gives me 0.167 molarity, and that's your H+ concentration. So as we've done in the previous problem, all you have to do is take the negative log of this using this equation right here. So you take the negative log by plugging in the number we just found in there, and then you know your pH. So in my calculator, the negative log of 0.167 ends up being, the pH is 0.777, keeping that 3 sig figs there. Right? If you have any other additional questions, let me know.